Hello, my name is Ricardo and I'm a member of the research team at Neuroelectrics. In this video, I'll present a study that we've performed entitled Improving Sham Protocols in tCS with Montage Optimization, actisham. So, as the name of the presentation implies, this study will be about sham methods for tCS. What happens when you turn on the stimulation device is that the currents in the electrodes, they ramp up over a period of a few seconds until a value that, in the case of tDCS, will be maintained unchanged until the end of the simulation. This will result in the induction of an electric field in the head, which will change the neuron's membrane potential, thus leading to the reported effects of stimulation. Now, in sham stimulation, the current ramps up as usual, but it immediately ramps down, thus leading to a null electric field in the head tissues, except for that brief period at the beginning and sometimes end of the simulation. The problem with this method is that the usual sensations under the electrodes that the subjects report in active stimulation, tingling or burning sensation, they are usually missing or decreased in sham stimulation. And this approach, therefore, does not effectively blind the subjects as well as one would want from a sham approach. So in this work, we had the objective of creating a new sham approach for tDCS that one effectively blinds the subject as to what type of stimulation is being done on him, and two, still, of course, doesn't have any effect on the brain following stimulation. So in order to do so, we will employ a montage optimization algorithm. Now, these algorithms allow for the determination of those parameters, in this case, the position and currents of the electrodes in the scalp, in order to effectively target a specific cortical area. These algorithms require a computational head model of a subject, which can be built from segmentation of structural MRIs into the most important head tissues. A 3D representation of the head with the electrodes is then created, we can use that 3D head, that's a reconstruction of the subject's head, we can use it to numerically calculate the electric field. We won't go into much detail here about the optimization algorithm that we used, but basically we applied the Steamweaver algorithm, which was developed here at Neuroelectrics. So this algorithm takes as inputs a target electric field map on the subject's cortical surface, which is related to the type of effect that we would like to have in a specific area of the brain. It then finds the montage that minimizes the difference between a weighted target electric field map and a weighted electric field map induced by the montage. This difference is calculated with this expression here, which is called ERNI, error with respect to no intervention. And when we applied this to one of the subjects that we use in this test, we see that we get an 8-channel montage that's targeting, in this case, this region, which is the left dorsolateral prefrontal cortex. Notice that in order to do this, we had to assume a relatively high electric field value on target. This is a target electric field value that we would like to have. And the positive signal here indicates that we would like to have an excitatory effect on this area. Let's imagine for now that we will place all of these positions of the active montage into a vector called X that has all the electrodes employed in the active montage. So one can imagine that in order to use this approach to develop a sham montage, we would just need to rerun the optimization with the target electric field set to a very low value, like 0.001 volts per meter or something. This would, however, return a solution with all the electrode currents set to 0, which wouldn't be very effective. We'd basically end up with the same problem that we started with. So instead of that, what we'll do here is to run one optimization at a time, only considered considering that one of the electrodes in the active montage has a fixed current of 500 microamps. We'll call that electrode the itchy electrode because most likely the sensory feedback that the subject will have will be under that electrode. Since we don't know which electrode is the best candidate for the itchy electrode, we will actually run 8 different montages. And for each montage, we will optimize for the Ernie expression, so we'll try to minimize Ernie, but set with a very low value of the electric field and imposing that the itchy electrode has a current of 500 microamps. So we will do this for all the positions in the active montage, and we will end up at the end with 8 possible optimized montages that they will all induce a very low electric field on target. So to select between one of these montages, we will actually choose the one that minimizes the average electric field on target, and in this particular case, it was the one that has AF3 as the. So on the left here, you have the active montage, and on the right here, you have the actisham montage. And as you can see, the actisham montage induces a very low electric field on target as compared to the active montage. And in order to do this, the actisham montage employs anodes and cathodes in an alternate pattern. As you can see here, there's this alternate pattern for the position of the anodes and the cathodes. And this pattern, what it does is that it maximizes the shunting of currents through the scalp between the electrodes. Now, shunting of currents is normal in tCS, and it happens because the scalp is a much better conductor than the skull underneath. However, we can maximize this by placing anodes with opposite electrodes with opposite polarity relatively close by. And ultimately, this is what explains the low electric field that's induced in this montage, even though the currents in some of the electrodes are still relatively high. So we've just shown that the actisham approach can be used to achieve a very low electric field on target, but still use currents that are relatively high, and therefore they will most likely generate some sort of sensory feedback from the subject. Since the montage in the actisham approach employs the same set of electrodes as the active montage, this approach is also very easy to integrate with double-blind protocols, so protocols in which both the subject and the operator don't know which type of stimulation is being done. And we have already applied this approach, the actisham approach, in a study targeting the primary motor cortex, and I highly recommend that you go and download and read this paper if you're interested in. So thank you for your interest in our work. Please send us an email with any comments, questions, or ideas. Don't forget we have a poster available with these results that you can also download and read in more detail, and visit us at neuroelectrics.com for more information about the company. Thank you, bye.